So today we are going to discuss the solution of system of linear equations. System of linear equations. Solution of system of linear equations. System of linear equations say they arise in a large number of areas. Both directly in modeling physical situations and indirectly in numerical solutions of other mathematical models also. These applications occur in all areas of physical, biological, and engineering sciences. Linear algebraic systems, they are also involved in optimization theory. So mathematics optimization theory have the least square, fitting of data, the numerical solution of boundary value problems for ordinary and partial differential equations, statistical inference, numerical solution of a system of linear equation, I would say they play a very important role. Numerical method for solving linear algebraic system, I would say it may be divided into two types. One is direct method and the second is iterative method. The direct method, direct methods are those which, in the absence of round off or other errors, yield the exact solution in a finite number of elementary arithmetic operations. Iterative methods, iterative methods, they start with an initial approximation, and then by applying a suitably chosen algorithm, they lead to successively better and better approximations. Iterative method, direct method, general form matrix notation, the general form. The general form of a system of m linear equations in n unknowns. Unknowns x1, x2, and so on, xn. Unknowns into xn can be represented in matrix form as we have the matrix form, the A11, A12, and so on till A1n. A21, A22, and so on till A2n. Sumlani A M1, this is M1, A M2, and so on till A Mn. This is m number of rows, n number of columns. Say the multiplying, so the m number of variables x1, x2, and so on till xn. This should be equal to some constants b1, b2, and so on till bn. This. So we can samjha laga C matrix को ना A करे, C matrix को ना B करे, sorry B है, sorry C matrix ना X करे, C matrix ना B करे. अदुना in short this can be written as A X is equal to B. That's why we have. where A is this matrix, X is this matrix, and B is this matrix. The solution of this system of equations give n values. It will give us n number of values, x1, x2, x3, xn, which satisfy this system of equations simultaneously. Adudagi ekoi nahawai consistent oi, adagi inconsistent oi haiba ama nahawai thingaramani school tamingida adudi karino haiba matamda a system of equations sigumba a system of equations is said to be consistent if it has at least one solution. If it has at least one solution ID, if we can determine the values of x1, x2 till xn. Sigi value mein amje we determine tonga magadi this system of solution is said to be consistent. And sometimes in some cases the number of solutions can be infinite also. Consistent. In some cases, no solutions exist. Then the system of these equations is said to be inconsistent. The system is said to be consistent. The system is said to be inconsistent. This system of equations is homogeneous. If all the B's, if all these B's are zero, B zero salaba, this system of solutions is said to be homogeneous. Otherwise, B khara zero chatraba, B khara, if some of the B are not zero, then in such a case, this system of equations is said to be non-homogeneous equation. What are we going to study today? Today we will consider only non-homogeneous system of equations, and then we will also restrict to those equations where m is equal to n. M is the number of equations, n is the number of variables or unknowns. So we are going to study those non-homogeneous equations, and we are going to study those cases where the number of variables is equal to the number of equations. Important property a non-homogeneous system of n linear equations in n unknowns. Number of linear equations ka number of unknowns. I repeat, a non-homogeneous system of n linear equations in n unknowns has a unique solution if and only if the coefficient matrix A is non-singular. If and only if this coefficient matrix A is non-singular. When we consider a set of n equations involving n variables, and all the B's, some of them are not zero. In such a case, this set of equations has a unique solution if this coefficient matrix, that is A, is non-singular. When is a matrix said to be singular? A matrix is said to be singular if
when all the elements on the matrix are equal to 1.
My determinant zero.
Determinant zero. A matrix is said to be singular if the determinant is zero. Those cases where the number of equations is equal to the number of variables. In general, for simplicity, we are going to study only those systems where the number of equations is equal to the number of variables. So M and N this A, matrix A will be a square matrix. Matrix is square matrix or any, and then for a square matrix, we can find the determinant. Non-singular matrix have those matrices whose determinant is not zero. Determinant zero matrix inverse inverse matrix singular matrix. So those matrices whose determinant is zero is said to be singular. They do not have inverses. But today we are going to discuss only those matrices which are non-singular. Only those matrices which can be inverted. So so minus system of equations we are going to solve the unknowns x1 to xn. Okay. Since since A is a non-singular matrix, then its inverse exists. And the solution of this system can be written as, see, left hand side when I multiply both sides by A inverse. When I multiply both sides by A inverse, AX equal to A inverse B. A inverse, this implies X equal to A inverse B. Matrix inverse, we can very simply multiply by the inverse matrix from the left and we get the solution. In case the matrix A is singular, then this system AX equal to B. Then this system has no solutions if all the B's are not zero. But if all the B's are zero, then it has an infinite number of solutions. I repeat, matrix is a singular matrix, determinant 0. If this matrix has determinant 0, case any case B zero, this system of equations has infinite number of solutions. Case singular determinant 0 determinant 0 B zero B zero B 0 then in such a case no solution exists. The method of solution of the system of linear equations may be classified into two types. Direct method ni, iterative method ni. Direct method are those methods which, in the absence of rounding of errors, they give the exact solution in a finite number of steps. Iterative methods iterative method we start with an initial approximate solution. Then iterative methods generate a sequence of approximate solutions which converts to the exact solution as the number of iteration goes to infinity. Iterative method they are an infinite process. We perform only a finite number of iterations, but iterative method they are infinite process, but we perform only a finite number of steps depending on our accuracy. Accurate we perform only a finite number of steps. So first let us study the direct method for specific direct method for solving such a system of linear equations. When direct method three special cases of three special cases have so that D has AX equal to B. If the matrix A is a diagonal matrix, then the solution is very simple. A matrix diagonal matrix solution line case matrix lower triangular matrix whatever. If this capital A, if this A is a lower triangular matrix, then we can easily solve this by I repeat, if A is a lower triangular matrix, then we can easily solve this system of equations by forward substitution. If this A is an upper triangular matrix, then we can easily solve this equation by a backward substitution method. Back substitution method. So high. How to express this A as a diagonal matrix or a lower triangular matrix or an upper triangular matrix. So then what is a diagonal matrix? Diagonal matrix have the
diagonal elements.
all the elements except the diagonal are zero. The diagonal element all the remaining elements are zero.
Zero.
Lower triangular matrix have the kind of
All the elements except the
diagonal
diagonal
left elements in there, they are not zero. All the elements on the right of the diagonal are zero. That is the lower triangular matrix. The upper triangular matrix upper triangular matrix have now all the elements on the left of the diagonal are zero. All the elements on the left of the diagonal are zero, and all the elements on the right of the diagonal are not zero. That is the upper triangular matrix. Okay. First, let us study a method which is called the Gaussian elimination method. The Gaussian elimination method. So let me write it on a new sheet of paper. So the first method which we are going to study is the Gaussian. Gaussian. Gaussian elimination method. ELIMINATI. Gaussian elimination method. Gaussian elimination method. Gaussian elimination method, I will say, it consists of two stages. In the first stage, the given system of equation is reduced to an equivalent upper triangular form using elementary row transformation. I repeat, in the first stage, the given system of equations is reduced to an equivalent upper triangular form using elementary row transformations. In the second stage, the upper triangular system is solved using back substitution procedure. I repeat, in the second stage, the upper triangular system is solved using back substitution procedure. In this way, we obtain the solution in the order xn no hana phangani, xn minus 1 phangani, xn minus 2 phangani, phangani, ultimately x1 last phangani. So let us study the Gaussian elimination method with an example. Example of Malaroga, we study the okay. Let me give you one example. This the Gaussian elimination method say solve the following system of equations using Gaussian elimination method. How the equation do it again? This is twice x plus 3y minus z equal to 5. This is 5. Next, 4x plus 4y minus 3z equal to 3. Matanga minus twice x plus 3y minus z equal to 1. So this is the system of equations, and we are going to solve this system of equations by the Gaussian elimination method. yaraba ado egadi solution combine hot kani solution di today we write it in matrix form the hana e receive ko ado egadi ekoi matrix form the e haragadi ekoi na line anaba first we start with the augmented matrix aduna says the we consider the augmented matrix. We consider the augmented matrix, that is sagi coefficient matrix ka constant matrix ba ani maksud function ba and perform the elementary row operations. On the augmented matrix. So I repeat, we consider the augmented matrix, that is coefficient matrix ka the matrix ka upon that is called augmented matrix, and perform the elementary row operations on the augmented matrix. Because the arithmetic operations that we're going to perform here will affect only the elements of the matrix A and the elements of the matrix B. So first, let us write down the augmented matrix for this given system of equations. So A, B, this augmented matrix is equal to is equal to coefficient matrix. So what is the coefficient matrix? The coefficient matrix is 2, 3, minus 1, 4, 4, minus 3, minus 3, minus 2, 3, minus 1. So this is the coefficient matrix. B, so B is 5, this is 3, this is 5, this is 3, this is 1. This is the augmented matrix. Okay. This is the augmented matrix. What is the next step? Next step, we perform elementary row transformations. We start with the first row. Using the first row, you try to eliminate the first element of the second row and the first element of the third row. So this elementary row transformation similar matrix. First row, you keep it as it is. 2, 3, minus 1, again, 5. Now, 4 is 0, chalan ki haragadi, row 2 is row 2j, this is row 2 minus 2 times row 1. 2 times row 1. When we perform this operation, row 2 is modified. How do we modify it? Row 2 is row 2 minus 2 times row 1. So 4 minus 2 times 4, 4 minus 2 times 4, this will be 0. 4 minus 2 times 3, this will be minus 2. Minus 3 plus 2, this will be minus 1. 3 minus 2 times 5, 10. 3 minus 10, minus 7.
So,
Yareko. So this is minus 2, minus 1, minus 7. R3 ki first element is 0. What is the operation that we need to perform? R3
3 plus R1.
R3 plus R1. R3 plus R1. So R3 plus R1 already. This will be 0. 3 plus 3. This will be 6. Minus 1, minus 1, minus 2. Already Kaitarani. This will be 6. Okay. Now using the first row, we have eliminated this the first element of the second row and also the first element of the third row. Next step to the Kaidarani. In the next step, using the second row ki first non-zero diagonal elements. Second row ki diagonal elements is we're going to make this element 0. 6 is 0. R1 length, you keep R1 as it is 2, 3, minus 1. R2 length 0, minus 2, minus 1. Sorry. Okay. 5. How many? Minus 7. How many? R2. So if I want to make this 0, I can R3 say R3 plus
2
3 times R2.
3 times of R2.
R3 plus 3 times R2. This is R3. R3 plus 3 times R2. So using the second row, you are going to make this 6 0. So this is 0 0. This will be 0. So 3 times R2, this will be 0. 3 times R2, this will be minus 3. Minus 3, minus 2, this will be minus 5. And then if we are going to add 3 times R2, so 3 sevens are 21, 21 plus 6, this will be 27. Yarba? Sige, data. So the 2, 3 minus 1 later, 0 minus 2 minus 1 later, 6. Sige 3 times with kindle. 0 pange. Hey, sige 3 times 21. This is 3 sevens are 21. 20 minus 21 minus 21 plus 6
Minus 15.
15. This should be 15. Minus 15. Minus 15. So we have done the stage 1 completed already. We have completed stage 1. Stage 1 completed already. Coefficient matrix A. This is the coefficient matrix A. Now we have reduced the coefficient matrix A to an upper triangular matrix. So we have reduced the coefficient matrix to an upper triangular matrix. So the stage 1 is completed. Then what is stage 2? Stage 2 is solution by back substitution. Solution by back substitution. Last row, look at the last row. Last row, last row is the minus
0,
5, minus 15.
minus 15.
minus 5 and 15.
So from the last equation, that regards equation from the it was zero. So we get. So what do we get? We get 2 3 minus 1 x. We get twice x plus 3y. So the x coefficient is y coefficient 3y so minus z. Minus z equal to 5 fange. This is 0 sakre. This is minus 2y minus z equal to minus 7 fange. Minus 5z equal to minus 15. So let us call it equation number 1, equation number 2, equation number 3. So this matrix, this augmented matrix, when we write it in equation form, we get this expression. Augmented matrix slice.
Yes, sir.
Okay. Next up, back substitution method. I think first Z solve our neighbor. First, we are going to solve Z. So from this equation, from equation number 3, from equation 3, we get, you divide both sides by -5. What do you get? We get Z equal to minus 15 divided by -5, which is 3. Using this value of Z, using this value of Z in equation 2, we get back substitution method. First Z solve next solve Z values. Now we will substitute this value in equation number 2. Z equal to 3Z. Now you substitute it in equation number 2. So what do we get? We get minus 2y minus 3 equals minus 7, which implies minus 2y. Don't have to get minus 2y equal to minus 7 plus 3 minus 4. This implies y equal to minus 4 divided by minus 2. This is plus 2. Yarba. So by substituting the value of Z we obtained in equation number 2, now we have obtained the value of y. Y hole y katare, y 2 tare. Z ne katare, Z ne 3 tare. Next time, using these values of y and z, we can solve x. So substituting these values of y and z in equation number 1, we can solve x. So using the values of these values of y and z in equation 1, we get equation 1 twice x plus 3y minus z. So twice x plus 3y. 3 times y, what is y? Y is 2. 3 times y minus z. Minus what is z? Z is 3. Z is 3. And z equal to, this is equal to 5. 5 comma. 5 comma. So this implies twice x equal to 3 into 2, 3 times 2, 6. 3 times 2 is 6. 6 minus 3, 3 tare. So plus 3 tare. Plus 3z, you bring it towards the right, it becomes minus 3. So 5 minus 3 is 2. So this becomes 2. So this implies x equal to 2 by 2, which is 1. Thus, we have solved the values of x, y, and z. Thus, the solution of the given system is x equal to 1, y equal to 2, z equal to 3. This is the solution. So this is Gaussian elimination method. Gaussian elimination method say Gaussian elimination method say you are given a system of linear equations. First we consider the augmented matrix A, B, have augmented matrix low row and perform elementary row transformation on the augmented matrix and try to reduce the coefficient matrix to upper triangular form. To convert it into upper triangular form, first first element ki first row ki first column the element to siznarga sigi second row ki first element amasung third row ki first element sigi 4 ga minus 2 ga se eliminate torani ka eliminate torani by using elementary row transformation. Alright, adu disi phange aduna elementary row transformation tawkanda you should also transform the values of b also. B should transform the ka aduna sigi a matrix tan natana b jona transform the ka. Next step no kaino using the diagonal element ka using the second element of the second row we try to eliminate the second element of the third row so that when we eliminate this it finally becomes upper triangular form so that when we eliminate this the coefficient matrix finally becomes upper triangular form the la name aduna see eliminate to ga di see is compared to row aduna see eliminate to ga di could row 3 dagi from row 3 we can add 3 times row 2 only then this will become 0 correspondingly sin minus 5 lani sig is minus 15 lani. Now at this step we have completed stage 1 to the lower end because we have converted it into upper triangular form. Next stage 2 la stage 2 the equation this equation in matrix form we write it in the equation form the matrix form to a variable x y z की form the equation first we solve z so line we can solve z very easily we get z equal to 3 then using this value of z we substitute it here and then we solve the value of y value kya phange y value 2 phange. Now we have got z equal to 3, y equal to 2. So we substitute these values in the first equation and then we solve for x. That is how we got the 3 values, x equal to 1, y equal to 2, and z equal to 3. This is a simple exercise. So this is, let me write it as page number 3. Do you want to look at another example? Another example of Yankizira Nakagamaka Chatarajira.
Chapman, bro.
Method Chapmanagani. Method Chapmanagani, another example of let me give it to you as your homework. No, you will try to so you say homework. Homework ni say the solve the following system of equations by using Gaussian elimination. Gaussian elimination method. Adrikaino for x1 plus x2 plus x3. This is equal to 4. Now, the x1 plus 4x2 plus plus this is minus twice x3. This is equal to 4. The minus x1 plus twice x2 minus 4x3 equal to 2. So that instead of saying x, y, and z, I have denoted the 3 unknown variables as x1, x2, and x3. And you have to solve the values of x1, x2, and x3 from this system of linear equations. And let me give you the solution so that when you do this homework, you get the correct answers. So from this, from this first we'll get x3 equal to minus half, minus half. Then using that value, you will solve x2. X2 also you will get half. So x2 is half. Using these two values, you will find the value x1 equal to 1. Okay. So here 1 half minus half. So give value of you try this at home and tell me if there is any problem here. the try toro, and if you face any problem, then we shall discuss it again on Monday. Okay. Adu ergadi koi saida sigi special case ama discuss torosi. Special case today partial pivot and apana pivoting to process am layer ko. Pivoting the process have say amu discuss torosi ko. We can apply this Gaussian elimination method to a system of equation of any order. I mean, it can have any number of variables, any number of equations. However, what will happen if any one of the diagonal elements turn out to be zero? Diagonal elements in this process, we finally obtained this. In this process, we finally obtained this. This diagonal elements, these are called the pivot, P-I-V-O-T, pivot coever. These are called the pivot elements coever. So what will happen if any one of these diagonal elements turn out to be zero? Suppose if this turns out to be zero, then division by zero is not defined. In such a case, we need to modify the Gaussian elimination method, and this process is called pivoting. P-I-V-O-T-I-N-G, pivoting to coever. Pivoting in this elimination process, if any one of the pivot elements, if any one of the diagonal elements vanishes or becomes very small compared to the other elements in that row, then we attempt to rearrange the remaining rows so as to obtain a non-vanishing pivot or to avoid the multiplication by a large number. Strategy pivot, P-I-V-O-T-I-N-G, pivoting. Pivoting is partial pivoting. I repeat, pivoting is of two types. One is partial pivoting, the second is complete pivoting. So first, let us consider partial pivoting. P-A-R-T-I-A-L, partial pivoting. P-I-V-O-T-I-N-G, partial pivoting. Partial pivoting have the kind of stage Gaussian elimination method pivoting and a procedure of Gaussian elimination method ki stage the first stage the obtaining the upper triangular form of the method of the coefficient matrix. So in the first stage of the elimination, the first column is searched for the largest element in magnitude, and this largest element is then brought at the position of the first pivot by interchanging the first row with the row having the largest element in magnitude. The first column do first column do the quite a chowa element element row duga first row duga interchange. In the second stage of elimination, the second column is searched. The first column with the largest element second column search the second column is searched for the largest element in magnitude among the remaining rows. Among the remaining rows that is leaving the first element, and then this largest element in magnitude is brought at the position of the second pivot by interchanging the second row with the row having the largest element in the second column. So pivoting to so let us look at one example. Example number solve the system of equations. X1 plus X2 plus X3 equal to 6 haibom lere 3x1 plus 3x2 plus 4x3 haibom lere this is equal to 20 adudagidi 2x1 plus x2 plus 3x3 this is equal to 13. So solve this system of equations using Gaussian elimination method with partial pivoting. Adogadi solution. First, let us try to solve the system. First, let us try to solve this system without pivoting. First, let us try to solve this system. Without pivoting. Pivoting to the Vidahana Koisiki system is solved on the and let us see what difficulty we face. Well, we have the augmented matrix that is A, B. This is the augmented matrix of Pyro. So the first element will be 1, 1, 1. 1, 1, 1. The 3, 3, 4. 3, 3, 4. The 2, 1, 3. 2, 1, 3. And then we have B, 6, 20, 13. 6, 20, 13. Now let us perform elementary row transformation. So this is similar to using the first element, first row first element seasonaraga I makhataba first column the makhataba elements is 0 chalangadoni ko. So 0 chalangadoni 0 chalangadoni adudi I have first row see hana it was madi kental lengaroi. It will remain as it is. Second row 3 0 chalangi hayagadi what should I do? R2 should be modified as R2 minus 3 times R1. Yaningra, if from this second row I subtract 3 times the first row, what should I get? I should get 0 here. 0 so I should get 0. 0. 4 3 times 1 I should get 1 here. 20 3 times 6 20 minus 18 I should get 2 here. And next move R3 2 0 first we multiply the first row by 2 and subtract from the third row so that this 2 becomes 0. So R3 minus twice R1. So this becomes 0 and this becomes minus 1 and this becomes 1. Twice this will be 1. Using the second element or the diagonal element of the second row, I should try to make this 0. And this one is 0. But we find that this pivot element, this diagonal element itself is 0. Diagonal element is 0. Upper triangular form the Ethiopia problem in the above matrix, the second pivot, the second diagonal element. This is the first diagonal element. This is the second diagonal element. So the second pivot has the value 0. has the value 0 and the Gaussian elimination method. Elimination method, procedure, PRO, and the elimination procedure cannot be continued further. Cannot be continued further. It cannot be continued further unless pivoting is used. Unless pivoting is used. Aduna project says the second row ki second column the elements 0 chakrabanina. A pivoting is another I see upper triangular form the so we should use pivoting. So let us use pivoting. So this is page number 3. This is page number 4. Pivoting system let us try. Let us try using it on a new sheet of paper. So, so now let us use partial pivoting. Partial pivoting. Partial pivoting. Partial pivoting system augmented matrix. This is the augmented matrix. Augmented matrix partial pivoting high. First column do first let us look at the first column. This is the first column. Look at the first column. First column is the elements. What is the largest element in the first column? The largest element in the first column is this number 3. The largest element in the first column is this number 3. Partial pivoting three rows. You should bring this second row to the first row. Second row first row interchange. You should interchange the second row and the first row. So in the first column, 3 is the largest element. Largest element, your row, second row. So let us interchange the first row and the second row. Partial pivoting in the first column, , 3 is the largest element. We interchange the first and second rows to get haraga. So let me write it here. Comparison. So what is the augmented matrix? This is the augmented matrix, and we are going to interchange the first row and the second row. So this AB becomes AB. It becomes, so first row will contain 3, 3, 4, 3, 3, 4, 20 jump. You should also carry 20 along with it. 3, 3, 4, 20. They see 1, 1, 1, 6 in the second row. So 1, 1, 1, 6. It comes in the second row. And the third row remains as it is. 2, 1, 3, 13. Then next step, we use elementary row transformation. We use elementary row transformation to make this and this 0. So 3 is 1, 2, 0. We use elementary row transformation. So this is similar to 3, 3, 4, 20 like that. So sigi 1 0 chalan gi kedowa R2 is combined modify to R2 is R2 minus 1 by 3 R1. R2 minus 1 by 3 R1. And I call R1 is 1 by 3 lower and then subtract from R2. So this becomes 0, 0 minus 1 by 3. And I call 0, 0 minus 1 by 3. This is minus 2 by 3. So mine using this 3 2 0 chalala. Gaussian elimination method to partial pivoting ID quite number row. So using this R3 combined 0 R3 first element combined 0 is R3 minus 2 by 3 R1. This will become 0. This will become minus 1. This will be 1 by 3. This will be minus 1 by 3. So now the first row is low. Second row is 0 chale. First row is first row is remaining row is remaining row is the second column. Now you check the second column of the remaining rows. Remaining row is the second column. Amana 0 ni, amana minus 1 ni. Magnitude to quite our numbers. Magnitude to quite our numbers minus 1 tareka. We are not going to consider the first row. First row is the interchange to first row is quite our now second row is second column second row is second column the first row is interchange. So now we are not going to look at the first row. Now we are going to look only at the second row and the third row. Second row and third row is the second column and easy compared. This is 0, this is minus 1. Which one is larger in magnitude? Magnitude minus 1 minus 1 magnitude 1. So this is larger. Siziga row 3 ziga row 2 ziga interchange in the second column. In the second column, 1 is the largest element in magnitude. 1 is the largest element in magnitude, leaving the first row. When the first row is the second row, third row, second column to compare to 1 is the largest in magnitude. Magnitude then we interchange. So we interchange. So say the third row the second row second row third row. So we interchange the second and third row. The second and third row. Third rows. Interchange A, B, this is equal to first row is so this will be 3, 3, 4, 20. Now we are going to interchange the second row and the third row. So this will be 0, minus 1, 1 by 3, minus 1 by 3. So okay, now 0, 0, minus 1 by 3, minus 2 by 3. Now, Now, after interchanging the second row and the third row, what do we see? We see that the coefficient matrix is already in the upper triangular form. Elimination clearly the resultant coefficient matrix is in upper triangular. It's in upper triangular form, and no further elimination is required. Elimination is required, and no further elimination is required. Now from this equation, from this equation, what do we have? We have the three linear equations. So what do we get? We get 3x1 plus 3x2 plus 4x3 equal to 20. Second row, second row we see that minus x2 plus 1 by 3 x3 equal to minus 1 by 3. Next, the third row, minus 1 by 3 x3 equal to minus 2 by 3. Now let us solve x3 first. So x3 hana solve. This is equation number 1. This is equation number 2. This is equation number 3. From equation 3, I can x3 equal to minus 2 by 3 divided by minus 1 by 3. This is 2. X3 is equal to 2. Now substituting this value, of x3 in equation 2, we get so this is the so the x3 later you put 2, we get minus x2 plus 1 by 3 into 2 equal to minus 1 by 3. This implies minus x2 equal to minus 1 by 3 minus 2 by 3. This is what? This is minus 1. So this implies x2 equal to 1. Minus x2 minus 1 already, x2 equal to 1. 1 using these values of x3 and x2 in equation 1. Equation number 1 is 3x1. So it is 3x1 plus 3x2. 3 times what is x2? That is 1. 3 times 1 plus 4 times x3. And what is 4 times x3? X3 is 2. This is equal to 20. So we get x1 equal to 3 plus 8. 3 plus 8, 11. 20 minus 11, 9. So this is 9 divided by 3. This is 3. Therefore, the solution is x3 equal to 2, x2 equal to 1, x1 equal to 3. Sineva. Aduna, according to Sai partial pivot. Let's call it 5. Partial pivoting high second. Partial pivoting the what is the new thing that we learned in partial pivoting? The new thing that we have learned in partial pivoting is that whenever one of the pivot elements is zero target, we should use partial pivoting. Partial pivoting the process it in the first step we look at the first column. First column first column we look at the first column. We look at the first column of the augmented matrix. Element element row, we interchange that row with the first row so that this row with the largest element becomes the first row. The first row is interchange. After interchanging, we get this matrix. Now, using this largest element, element and is zero using elementary row transformation. Step next time, row ani lemhori. However, row ani is the pivoting among the second column do among yang. First row we are not going to touch the first row again. Second column do among yang. Second column is the quite chow in magnitude to yang. Quite chow magnitude to 6 so second row the quite chow magnitude third row the later. Now we interchange the third row and the second row. After interchanging the third row and the second row, 0 0 already in upper triangular form the later. Elimination stage 1 is complete. Karigumba 0 or Equina Hana Tokiba Dumaina, Sigi, second element, second row is second element, elementary row transformation Targa, 0 Salhanganever. Third row is second element, 0 Salhanganever. If it were not 0, so 0 or Mregati, Equihana Tokiba Dumaina, second row is second element, elementary row transformation will make it 0. But since it is already 0, we stop the elimination process here and then we go to the back substitution process. The back substitution process that came to Hong money. So pivoting is no pivoting is no only in the first stage. First stage the man of Hongbani at Makatava back substitution method that the man of Hongan. Okay, this is page number 5, this is page number 6. Discuss okay. Next, Gauss-Jordan method. How to find the inverse of a matrix. How to find the inverse of a matrix by using Gauss-Jordan method. So you see, we will discuss an example. We'll understand it better. Say the Gauss-Jordan method to find the inverse of a matrix. So the combined togi haibu, we will be given a square matrix. We will be given a square matrix A hypermatrix. We will be given a square matrix A. Already next step we augment the matrix A by the identity matrix. A is the same order level identity matrix. Then, using elementary row operations on this augmented matrix, we reduce the matrix A to the identity matrix form. Gauss-Jordan method Gauss-Jordan elementary row operation A say identity matrix form identity matrix form identity matrix this will become the inverse of the matrix A I repeat, using elementary row operations on the augmented matrix, we reduce the matrix A to the form I, and in the process, the matrix I is transformed to A inverse. This is Gauss-Jordan method. Very simple example. Very simple method. We can consider one example. Example to discuss. We can stop for the day. So, example to find the inverse of the matrix. Find the inverse of the matrix A. 3, 1, 2, 2, minus 3, minus 1, 1, minus 2, 1. Sigi matrix sigi inverse putho using Gauss-Jordan method. Gauss-Jordan method. Using Gauss-Jordan method targa. The resolution. Using the augmented matrix. Using the augmented matrix. Matrix is the identity matrix. Identity matrix we get A identity matrix. This is equal to 3, 1, 2, 2, minus 3, minus 1, 1, minus 2, 1. Similarly, and what is the identity matrix? The identity matrix is 1, 0, 0. Same order. So 3 by 3 identity matrix 3 by 3 0, 1, 0, 0, 0, 1. Already first using the first row, first row first element 3 is 2 go 1 is 0 so 3 1 2 so okay 0 elementary row transformation identity matrix form identity matrix form 3 is 3 over 3 is 3 over identity matrix this diagonal element should be reduced to 1. So what is the first step? First step is to divide the first row by 3. So when I divide the first row by 3, this 3 becomes 1, and this 1 becomes 1 by 3, and this 2 becomes 2 by 3. Then I say identity matrix I see 1 talani, so 1 by 3, 2 by 3. So we are dividing the first row. First row is changed. This is first row divided by 3. So this becomes 1 by 3, 0, 0. 1 by 3 divided over the 6 yonika. Select 2 minus 3 minus 1, 0, 1, 0, 1 minus 2, 1, 0, 0, 1. Select. Next step. In the next step. Using the first row, first element, I see 2 go 1 is 0. So this becomes 1, 1 by 3, 2 by 3. So I R2 modify R2. Say R2 minus 2 times R1. So this becomes 0. This becomes minus 11 by 3. This becomes minus 7 by 3. This is 1 by 3. This becomes 0. This becomes 0. 0 to 0 R2 minus twice R1 so minus twice R1 this will be 0 minus 2 times this will be minus 2 by 3. 1 0 R3 so 0 R3 R1 R3 minus R1. So R3 minus R1, what will we get? This will become 0. This will become minus 7 by 3. This will become 1 by 3. This will be minus 1 by 3. This is 0. This is 1. Sigi process lore. Already among si 1 tahange. Si among 1 tahange. Haragadi pedorani. Si among 1 tahange haragadi. We should divide the second row throughout by minus 11 by 3. So we are going to divide the second row throughout by minus 11 by 3. So this is similar to first row zero thamani 1 by 3, 2 by 3, 1 by 3, 0, 0, 0, and this will be divided by minus 11 by 3. So this will be 1, and then this will be 7 by 11. 7 by 11. This will be 2 by 11. This will be minus 3 by 11. This will be 0. We keep it as it is. 0 minus 7 by 3, 1 by 3, minus 1 by 3, 0, 1. So what have we done here? We have divided R2. We have divided R2 by minus 11 by 3. Next step, next step. Show me on. Next step, using this element, second row, second element, using this element, we are going to make this 0, and not only this 0, we are also going to make this 0. Matatu 0 using this element by elementary row transformation. Because ultimately I want this to reduce to an identity matrix. So what will remain unchanged? The second row will remain unchanged. 0, 1, 7 by 11. Second row is 2 by 11, 2 by 11, minus 3 by 11, 0. First row is first row the C0 from first row we subtract 1 by 3 times row 2. So from R1, R1 minus 1 by 3 R2 1 by 3 R2. Already C0 will add 7 by 3 R1. Sorry, R2. R3 C0 R3 plus 7 by 3 R3 plus 7 by 3 R2. So using this second row, we are going to make this term 0 and this term 0. Sige operation aninji toraga. Adudi side kari phangani. So 1 dagi 0 gi any factor khaidodi, it will still remain as 1. This will become 0. This will become 5 by 11. 5 by 11. This will become 3 by 11. This will become 1 by 11. This will be 0. So the second row, the third row, the 7 by 3 this will remain as 0. This will be 0. And this will become 20 by 11. This will become 1 by 11. This will become minus 7 by 11. This will remain as 1. Yare. Next step, next step, I want to make this to an identity matrix. So I should divide the third row by this quantity. So this 1, 0, 5 by 11, 0, 1, 7 by 11, 0, 0. I am dividing the third row by this quantity. So this will become 1. This 3 by 11 is unchanged. 1 by 11 is unchanged. 0. 2 by 11 is unchanged. Minus 3 by 11 is unchanged. This is 0. Now I'm going to divide throughout this by 20 by 11. So this becomes 1 by 20. This becomes minus 7 by 20. This becomes 11 by 20. that is R3. This is R3 divided by 20 by 11. Next time, next step, using this element, I'm going to make this and this 0 by elementary row transformations. So using this element, I'm going to make this and this 0 by elementary row transformation so that this becomes the identity matrix. So the IC row 3 0 0 1 1 by 20 minus 7 by 20 11 by 20. This will be unchanged. From row 1, what are we going to subtract? Row 1 this is row 1 minus 5 by 11 row 3. 5 by 11 row 2. This is row 2 7 by 11 row 3. From row 3 we are going to subtract 7 by 11. From row 2 we are going to subtract R2 minus 7 by 11 row 3. So when I 1 0 any factor this will be 1 0 journey 0 because of this operation. 1 0 0 and this will become 1 by 4 minus 1 by 4. And this is 0 1 7 by 11 times this this will become 0 and this will become 3 by 20. This will become minus 1 by 20. This will become minus 7 by 20. Now this equation is in this equation is in I A inverse form. Jordan method, Gauss Jordan method. By elementary row transformation, we transform this A to identity matrix, then this I automatically transforms to A inverse. So this is A inverse. So therefore A inverse is equal to this thing 1 by 4 minus 1 by 4, then 3 by 20 minus 1 by 20 minus 7 by 20, then 1 by 20 minus 7 by 20 11 by 20. So this is the inverse. This is the inverse of the given matrix. This A matrix inverse. This is the inverse. So the lower step. But this is simple. Idea is simple. Gauss elimination method target to Gauss elimination method coefficient matrix to upper triangular matrix coefficient matrix upper triangular matrix Gauss Jordan method coefficient matrix identity matrix identity matrix by using elementary row transformation, and in this process the identity matrix on the right it transforms and ultimately it becomes A inverse. So this is how we can find A inverse using elementary row transformation by Gauss Jordan method. So let me stop the recording here.